Yep, this week we're going to see where coins go when you put them in a vending machine. We're going to go to a high-tech body shop too. They'll probably make me stay outside. First though, here's why electronic things are getting smaller all the time. I think doggy treats are getting smaller too.
My career in electronics has only spanned about 20 years, but in that time, I've had to throw away everything I knew and start over. Twice. Electronics deals with electric currents that change values, usually rapidly. And various components act on those rapid changes in different ways. A lot of electrical components are passive. No matter what they're doing in the circuit, there's some sort of a net loss. Base and treble controls are good examples of passive devices. An active device contributes some sort of a gain, and a good example of gain is an amplifier stage. Wind it up. This single vacuum tube amplifier just took tiny electrical wiggles from this phono cartridge and amplified them so they were big enough to wiggle a speaker cone. Now, if you just accepted that statement, I think we better pause. Because how can a device give out more than it took in? You can call it magic and go make a sandwich, or you can look at the basic amplifier more closely. The active device here is a good old-fashioned vacuum tube. The British call these things valves, and that's a pretty good description. The term amplifier is mostly a lie. Nothing really gets amplified. The tube allows a tiny wiggling current to control a larger current from another source of power. So the output of the amplifier really consists of a larger image of the input signal. The input signal isn't really made bigger. One of the nice things about tubes is they were easy to explain. Inside is a heated metal element that emits electrons. A short distance away is a positive metal plate. Now, because of the electrical charges in the heater, electrons flow from the heated element to the positive plate. The flow of those electrons is an electrical current. In between the two elements is a fine wire mesh. As the electrical potential is changed on the mesh, the flow of electrons is influenced. As the mesh is made more negative, the flow of electrons is reduced. Now, all this would be merely interesting, except for the fact that a very small change on the mesh can control a much larger current. Depending on the way those initial currents are adjusted, the tube can either create a larger image of its input signal, that's called analog or linear operation, or it can be made to switch totally on or off. We used to call switching totally on or off switching. Now we call it digital. When you look at the vacuum tube overall, it's pretty inefficient. It's large and requires quite a bit of power to heat it up. But we shouldn't be too hard on the vacuum tube. It gave us radio, television, computers, music, and all other electronic wonders. The transistor gave us television, radio, computers, music, and all other electronic wonders much smaller, cheaper, and better. The transistor does the same job as the tube. It allows a tiny current to influence a larger current. It's small, cheap, and efficient. Hey, just a second. Come back here. There's one very bad thing about transistors. They're almost impossible to explain. The official explanation requires us to take several odd quirks of physics on faith, and it also requires a textbook to open on the table. You can be comfortable with transistors without knowing exactly how they work. I am. There are a few different constructions of transistors, but they all rely on classes of metals called semiconductors. The simplest transistor is a junction of 3 pieces of semiconducting material. One of the most famous of those materials is silicon. And it's made into a semiconductor by, as my encyclopedia says, the careful placing of impurities. Let's leave it at that, I think. The transistor is an active device with 3 connections. A small current flowing this way will influence a larger current flowing here, much like the old vacuum tube. You'll note, by the way, that my current flow isn't going in the direction of the arrow. Well, to this day, our schematic symbols all point the wrong way. See, Ben Franklin had a 50-50 chance of guessing right on the flow. Nice try, Ben. Transistors don't require heat to work, so they're more efficient than tubes. They're obviously a lot smaller, and as far as the price goes, I paid 3 cents for this one. Of course, I had to buy 100 of them to get that price, but I'll use them for something. Vacuum tubes required several hundred volts for their operation, but transistors will work well on a few volts. Because of that ability to work at safe voltages, I can demonstrate just what it means to be an active device. This transistor is all set to flow its large current through the light bulb. Here's the schematic. I'm going to supply a small current to it with my body, where the arrow is on the schematic. Now, because the current I'm supplying is so tiny, I'm not feeling any heat. And because the voltage is low, I'm not getting a shock. The transistor, though, is feeling heat because of the relatively large current it's supplying to the light bulb. Heat is the big enemy of transistors. Transistors that do hard work, like driving the speakers in your hi-fi, are physically larger, often mounted on heat radiating things like this. No matter how large the container is on a transistor, the actual transistor inside is very small. So, I guess it was just a matter of time. The integrated circuit takes the careful placing of impurities to new heights. Since individual transistors are very, very tiny, they can be made by the thousands on small slabs of semiconducting material. And by the careful placing of impurities, whole circuits can be fabricated. The small slabs of material are called chips. In describing chips, it's common to proclaim that there are thousands of transistors on this chip. Well, that brings up a kind of an interesting point. A simple transistor radio can make do with 6 transistors. The integrated circuit version of this needs 100 transistors. Transistors require various other components to function, and most of those components have to do with setting proper current flows around them and things like that. Transistors are easy to fabricate on chips, but a lot of the other components aren't. So, most integrated circuits use extra transistors to simulate the other components. Chips are one of the only things in life where the extra complexity costs nothing. This is the central processing unit for a personal computer. Now, all chips are not microprocessors, no matter how often the media get it wrong. A computer may have a lot of chips, but only one microprocessor. That particular one is the 6502. It writes the Acme scripts and does the housekeeping for the show. It contains upwards of 1,000 transistors, and it's pretty expensive as chips go, $2. Now, as manufacturing gets better, more and more circuitry gets crammed on silicon chips. Here's one of the latest breed of microprocessors. It's a Motorola 68,000. It does all of the Acme graphics. Here's the, these little things are so tiny. There's the chip that's inside. Here's a picture of it with its chip inside. Here's the silicon wafer that they come off of. It has a lot of chips on it. Here are a couple other microprocessors in different packages. And in case we have a scoop, in case you want to make your own chip, we scored on one of the original drawings from a chip of that size and complexity. We'll hold on it for a few seconds in case you want to take notes.
Gunner, sail down.
The modern automobile is a complex mechanism made from lightweight materials for fuel efficiency, yet designed to protect the occupants in a collision. Designed crumpability. When one of these precision machines is redesigned suddenly by the force of a collision, the repair job is much more complex than a few years ago. The last generation of cars used a heavy frame. The framework supported the engine, drivetrain, and suspension. These cars could actually be driven without any fenders, doors, or panels. Modern cars use a unibody concept. The fenders, doors, panels, and even the glass are structural components that work together to support the drivetrain and suspension. As well, the overall strength of the shell is due to the geometry of its parts, not just the strength of the steel. The proper name for unibody, by the way, is monocoque, the word and concept borrowed from aircraft design. The monocoque body protects the passenger compartment by absorbing impact all over. This makes assessing damage to one of these cars fairly scientific. Damage has to be undone in the order and direction that it was done, with care taken to restore the original strength and crumpability in the event that it's hit again. The front of this car is badly damaged, but it's important to begin by finding out what's bent on the entire car. Measurements are done using the manufacturer's data and an imaginary line under the car called a datum line. In this case, a laser measuring system is going to be used, so targets are hung from holes in the body. These holes are the same ones that the factory used to build the body in the first place, and their height and spacing from the datum line are known exactly. The laser projects a horizontal and vertical sheet of light. This creates an accurate cross on any object in its path. Once the targets have been installed and the laser aligned, what's bent reveals itself. Above the car, other measuring devices check critical locations. Here are the front suspension attachment points. The car is set up on special stands that allow the body to be pulled in any direction. This particular equipment can be configured to pull from any angle in any plane, even a complex pull in two directions at once. This is important to pulling out the damage along the exact lines of impact. The pulling is done by powerful air-operated rams. As you might expect, a pull is made a little past the mark, and as the tension is relaxed, the metal springs back. Today's lightweight cars are made from high-strength steel that needs special care. Stress has to be relieved, and any heating has to be done carefully to avoid destroying the molecular arrangement of the high-tech metal. Ripples and recesses put in by the factory have to be preserved, and any welding has to be done with special equipment. Even though some of these parts aren't visible on the finished car, for safety, they'll have to be replaced. When the body shell's been repaired correctly, all of the visible parts will fit perfectly. More importantly, the front end alignment will be correct. And most importantly, the car will still protect the passenger compartment in the event of a second collision. Like collision repairs of the past, minor dings and dents are patched, smoothed, and painted. And also, like the successful collision repairs of the past, she'll look good, too.
Hey, why don't we do a thing about cheese?
The first coin-operated vending machine dates back to 200 BC, when Hero of Alexandria described a coin-operated device that dispensed holy water in an Egyptian temple. Wonder if they kicked it when it failed to dispense. I have the world's simplest vending machine here. Take a candy, leave me a penny. Now, it's not the function of the Acme school to make sad commentaries on contemporary society, so let's just jump past the rest of that example to the fact that in my vending machine, I need to ensure that you left me a coin, I need to determine its denomination, and I need to make sure it's a coin, not some round thing you found in the basement. I need to count the coins, and if I want to sell even more candies, make change. If I want to be nice, I'll have my machine give you your money back if I'm out of candies or if anything else goes wrong. If I want to be real nice, I'll give you the chance to get the coins you inserted back if you find you don't have enough change to make the whole amount. A lot of vending machines won't forgive that mistake. This unit is found in millions of vending machines. The heart of it's what used to be called the slug rejector. Nowadays, they call them coin acceptors. A happy commentary on contemporary society. Don't try to slip them a slug, though. They'll reject it. It's a slug rejector, coin acceptor's job, to verify that the coins are genuine and to sort them into nickels, dimes, and quarters. Sometimes 50 cents and dollars. This unit only handles nickels, dimes, and quarters. The sizes are sorted with rotating cradles arranged in order of size. A quarter will tip this top cradle. Nickels and dimes fall right through, and nickels tip the second cradle, and dimes fall through to the third one. Anything smaller than a dime, shame on you, will fall through to the coin return. And an extra widget on top of the quarter cradle will reject anything larger than a quarter. Shame on you again. After the coins are separated by the cradles, they roll down inclined planes and undergo various tests. The details vary from unit to unit, but a combination of levers and carefully placed bumpers check the coin for weight and type of metal. If the coin doesn't pass these tests, it falls into the coin return. Some of the things that the acceptor rejects will get stuck in it. That's where this comes in. This lever is connected to the coin return button. It opens up the acceptor and wipes a finger through the places where things might get stuck. The unit fits in here. These fingers are controlled by the coin return electromagnet. If all's well with the vending machines, the fingers are held out of the way by the electromagnet. If the machine's out of product, or if it's unplugged, the fingers poke into the acceptor unit and force all the coins to be returned. Switches located under the nickel, dime, and quarter slots activate each time one of those coins passes. This bank of switches sets the price for vending. Going from left to right, they're equal to 5 cents, 10 cents, 20 cents, 40 cents, 80 cents, and $1.60. Various combinations of the switches will give any amount from 5 cents to $3.20. This one's set for 15 cents. Now, when you start inserting coins into a coin unit, they drop immediately into the cash box. So if you want to abort the transaction, the coins are no longer available. Some machines that take a lot of coins, like cigarette machines, will hold your coins in escrow and return them to you if you push the coin return. These tubes are where your change comes from. If the tube isn't full, inserted nickels will drop into the tubes instead of the cash box. If the tubes are full, a flap redirects the nickels into the box. When it comes time to make change, a motor underneath dispenses the correct number of nickels into the coin return. There's a switch at the bottom of those tubes that lights the use correct change light. Pretty neat, but technology marches on. If you're in the coin business, one thing you notice is that those pesky governments keep changing the coins, their size, their metal contents, their value. This one's the high-price model. It takes the new dollar coins, too. The acceptor has been simplified to 2 infrared light beams and a metal detector. The time it takes for the coin to break the 2 light beams on its way past tells the machine whether it's nickel, dime, or quarter-sized. The metal detector, hiding under the plastic there, makes the final decision, much the same way that most metal detectors will ignore valuables and find junk on the beach. This one has inventory tubes for nickels, dimes, and quarters. It'll attempt to make change in the most efficient way. If it owes you 30 cents, it'll try to give you a nickel and a quarter. If it's out of quarters, it'll try 3 dimes. And if that fails, it'll dump a load of nickels on you. It'll even pay you back for coins in the cash box. This connector interfaces with the dollar bill acceptor. Now, no discussion on coin acceptors would be complete without a detailed discussion of the dollar bill acceptor. Well, I can't tell you about the dollar bill acceptors because they won't tell me about them. Apparently, they're not quite as foolproof as the coin acceptors. Little knowledge is a dangerous thing. So, tune in next decade. Paper money will be obsolete, and we'll take a look at how the dollar bill acceptor worked. How long do you figure these half-hour shows are? Well, they're 24 minutes. Television. Go figure it. Making shows run to time's an interesting process. In the old days, I used to write items with a pencil and paper, and I discovered that a pencil would last for about 60 seconds worth of dialogue before it needed to be sharpened again. So if I was writing an 8-minute item, I'd sit down with 8 sharpened pencils. The method worked perfectly. Nowadays, of course, I use a word processor with a direct readout of the number of words and pages I'm using. I love it, but something interesting's happened. In the old days, I used to make spelling mistakes. Now a word processor can fix those. But the word processor gives you the power to make sweeping, huge, horrible grammatical errors. They usually come about by correcting part of a sentence and neglecting to read the rest of the sentence by part the whole, usually grammatical too often, if you catch my drift. Now, word processor errors aren't simple typos. They're much more bizarre. So from now on, I want everyone to call them WORPOs. Now, to make these shows run to time requires a plan. And rather than cut out interesting stuff, we have a small section of padding built in. And if the show runs short, I come on at the end and fill the missing seconds with some generally useless pieces of information. 4, 3, 2, 1, out.